first example involving the dot product, we have this following questions, or rather question part. Refer to the origin O, the points A and B have position vectors A and B respectively. It is given that mod A, or rather the magnitude of vector A is 3, magnitude of vector V is 5, magnitude of vector 3A minus B is 10. And they want us to show that A dot B equals to 1. Alright, so this is a dot product, A dot B equals to 1. So you might not know what to do here, right? So we want to prove A dot product. So this thought process is you want to prove that A dot B equals to 1. And since we have mod A, mod B, let's try maybe trying to find A dot B equals to mod A mod B cosine theta. Problem is that we don't know what theta is. Alright, so this method is impossible. Alright, so we cannot use this mod A mod B cosine theta. That wouldn't work because we don't have theta. What else? Alright, so oddly enough, they gave us 3a minus b equals to 10, right? Mod 3a minus b equals to 10. So we should use that, alright, because it's kind of random to give us, alright, 3a minus b, the magnitude of 3a minus b equals to 10. So what can we do here is actually, how do we relate the dot product with the modulus, alright? Now, is there a point of doing the definition of, let's say, involving the modulus? Answer is no, alright, because that will require an angle. So we can't use the definition of modulus of first vector, modulus of second vector, and the angle between two vectors. What else? Alright, it actually comes from the property that we learned in the previous video, where if we recall, if we were to dot the same vector, so let's for example say c dot c, it equals to mod c squared. So this is one of the other ways, and actually the main ways, to actually also involve modulus and the dot product, right? So if we have, let's say, vector 3a minus b dotting itself, we know that this equals to mod 3a minus b squared, and it is 100. Then from here we involve the other property, right? The aka the rainbow method, but it's really just expansion. Alright, so we have 9a dot a, so which is mod a square, plus, now minus b times minus dot minus b, so we get minus has become plus, then mod b square. Then minus b dot 3a, so minus 6a dot b, alright, because we're gonna do it twice, alright. So this is kind of very similar to, x plus y square equals to x squared plus y squared plus 2xy. This equals to 100. We know that mod a is 3, so mod a squared is 9 times 9, 81. Mod b squared is 5 times 5, 25, minus 6a dot b equals to 100. This gives us 106. Rearranging, 106 minus 100 equals to 6a dot b. We have successfully proven that a dot b equals to 6. Alright, so this is how, rather a dot b equals to 1. So this is how we can prove, or we should prove, that a dot b equals to 1 by considering the modulus, but not in the sense of the definition of mod a and mod b cosine theta, because we don't have any angles, but instead using this very important property right here. Alright, so I mean, obviously don't write this in because vector c is undefined. So that's for part 2. How about part 4? Thing is very different, it's nothing to do with dot product, but instead revisiting the idea of collinearity. Alright, given that vector a, vector 2a plus 3b, and vector mu a plus 2b are collinear, find mu. Alright, so we already know that if they are collinear, then they are parallel, right? So let's say we have the first vector, 2a plus 3b minus a, right? Because they must go in a particular direction, we have a plus 3b, which means that the first direction vector, so let's say this is point a, and then this is point 2a plus 3b. Then obviously this vector here would then be parallel, and in fact lie on the same line as, let's say this is mu a plus 2b, must be lying on the same vector or parallel to from here to here or from here to here. Alright, so what we can do is very simple, right? Make it the easiest. The other is mu a plus 2b minus a must be parallel to a plus 3b and hence a scalar multiple of a plus 3b. Alright, because they must be going in the same direction, just with different lengths. So we have mu minus 1a plus 2b equals to ka plus 3kb. Alright. So from here we just compare the coefficient, right? Quote unquote comparing coefficient. 3k equals to 2, k equals to 2 over 3. Mu minus 1 equals to 2 over 3, and finally mu equals to 5 over 3. Alright, and that's the value of mu. Alright, so this is the idea of using the dot product, and also in a way sort of a revision for our collinearity, where if we have 3 points, let's say this point A, point B, point C. Let me try to fix a bit. Then we obviously know that if this is point C, then the vector A to B must be a scalar multiple of the vector A to C or B to C, and vice versa. Alright, so this is how we can solve these questions for dot product and collinearity.